Hello. We have now covered all of the material for Unit 2 in CHY 113. And so since this unit really covered a lot of material, and so I wanted to just put together something to sort of recap everything in the unit and just take a look back at everything that we have covered and try to tie it together a little bit. And so this entire unit focused on several different aspects of chemical reactions and chemical equations. We began just by looking at how we represent chemical equations in general, or how we represent chemical reactions with chemical equations, and how we can either just sort of use a word equation and describe what's happening, and just say that, for instance, methane reacts with oxygen in order to yield carbon dioxide and water, or we can write out the actual chemical equation and depict what's happening with our reactants reacting to yield our products. And so we can get that symbolic representation of a chemical reaction through writing out our chemical equation. From there, we talked about how important it is to balance equations in order to satisfy the law of conservation of matter. And so we have to remember that during the course of a chemical reaction, the reactants are going to be broken up in some way. And so the combinations that reactants exist in are going to be broken up and then form new combinations in the products. And those combinations are going to be dictated by everything that we've learned about putting together chemical formulas. And so the ratios that exist in our reactants might not be the same ratios that exist in our products. And so, for instance, if we have MgCl2, perhaps as a reactant, but things get recombined and we perhaps form silver chloride, AgCl, as a product, then we have that discrepancy with our CLs. We started with two chlorines because we were told that it was MgCl2, so it had to be Cl2. So that's how the ratio works with magnesium. But now with silver, we only have one chlorine, silver chloride, AgCl. And so the law of conservation of mass, though, tells us that that extra chlorine couldn't have just disappeared. It had to have gone somewhere, which tells us that instead we were going to form two AgCls, which would have also meant that we had to start with two silvers. And so that's where balancing equations comes from, is the fact that we're going to have new ratios of our elements on the product side as compared to the reactant side. And so we have to balance that out. We talked about how once we write the equation, we do not change the subscripts. Remember, those subscripts are related to the ratio that has to exist to satisfy that particular combination of elements. We can, however, change the numbers in front, and that's how we balance equation, is by using coefficients in front of our equation, or in front of our various compounds, rather. And so, for instance, in the equation we just looked at, the combustion of methane, we saw that we don't have our hydrogens, for instance, are not balanced. 4 on our reactant side, 2 on our product side. Likewise, oxygen, 2 on our reactant side, 3 on our product side. And so we have to fix that somehow. And so we can adjust that by having 2 O2s and creating 2 waters. So then now we have 1 carbon on each side, 4 hydrogens on each side, and 4 oxygens. Now the law of conservation of matter is satisfied. We have the same number of every type of element. And then we did some other examples. Feel free to pause the video here if you would like and balance these equations, remembering that we have to have the same number of each type of element on both sides of our equation. So pause the video now if you want, and balance these equations. And hopefully this is what you were able to come up with. Now we have 3 correctly balanced equations. Next, we moved on to start talking about different types of chemical reactions. And we had this conversation around what the driving force of a reaction is, or what some driving forces of reactions might be. There are several different factors that might serve as a driving force, that might be the reason a reaction even occurs. Things like, we talked about precipitate formation of weak electrolytes, formation of gases, or if there's a favorable redox change. We didn't necessarily talk about what makes something a favorable redox change or not. That's sort of beyond the scope of this particular course. But we did look at redox reactions in general. But the reason that they do happen is because the change in oxidation numbers is favorable for various reasons. And so first, we had looked at precipitation reactions. So for instance, a reaction between aqueous lead nitrate and aqueous potassium iodide forms aqueous potassium nitrate, but solid lead iodide precipitates out of this reaction. Another example, aqueous barium chloride plus aqueous sodium sulfate. We mix the two of those together. We then have solid barium sulfate precipitating out and some aqueous sodium chloride in our solution. And we talked about how we determine precipitates from using our solubility rules. And we have those listed right here. You will not need to have these memorized for the upcoming exam. You will have access to these solubility rules. You will have to know how to use them, but you will have access to these rules. And so remember that we use these solubility rules to see if our new combinations, our new products, to see if any of those are insoluble and will precipitate out as solids. And so for instance, if we have calcium carbonate as one of our predicted products, we find where that is or what set of rules would govern calcium carbonate. And we see that we do have a set of rules here concerning carbonates, that most carbonates are insoluble. Most carbonate compounds will be a solid. There are some exceptions. If ammonium is our cation or any of the alkali metals, but calcium is not an alkali metal. Calcium right here is one of the alkaline earth metals. So calcium carbonate is not one of the exceptions. Therefore, calcium carbonate would be a solid. And so it would precipitate out of any sort of reaction. We talked about how we can then put together a net ionic equation showing the formation of solids and taking out our spectator ions. Remembering that spectator ions are simply ions that don't take part in the actual formation of the solid. And so in our example here, we had ammonium carbonate plus magnesium iodide forms ammonium iodide and magnesium carbonate. That's our balanced molecular equation. From there, we come up with our ionic equation, separating out all of our ions. And so 2 NH4 pluses plus 1 CO3, a magnesium 2 plus and 2 I minuses. And then on our product side, 2 NH4 pluses and 2 I minuses, plus our magnesium carbonate, which is together as a solid as determined by our solubility rules. Then we crossed out any of the spectator ions, anything that remains aqueous on both sides of our equation. And then we were just left with our magnesium plus our carbonate forms our MgCO3. And there's our net ionic equation for this reaction. We then turned our discussion towards acids and bases. Define acids as any species that increases the concentration of H plus in solution. They ionize, typically most acids will ionize to form H plus. And so for instance, HCl will dissociate and ionize into H plus and Cl minus. And we discussed that H plus is really just a proton. When we talk about a hydrogen 1 plus ion, what we're really talking about is just a lone little proton hanging out. And so acids are typically called proton donors. We talked about some of our properties of bases. That bases, one of our definitions, are that they are any species that increase our concentration of OH minus. And that bases, typically, especially the strong bases, ionize in aqueous solution to form OH minus. So for instance, sodium hydroxide, NaOH, will dissociate into its ions, Na, sodium, and OH minus. And so we get more OH minus that in that way. And we talked about for one of our definitions, that bases are also proton acceptors. So anything that accepts a proton would be labeled as a base in that particular reaction. And when we looked at acid-base reactions, so for instance, the sort of a classic acid-base reaction of sodium hydroxide plus hydrochloric acid forms aqueous sodium chloride and liquid water, making the driving force for this particular reaction is the formation of water here, the formation of a weak electrolyte. In a net ionic equation, our OH minus plus our H3O plus forms two H2Os. And this net ionic equation applies to all strong acid, strong base reactions. Another way to think of this, remember we also talked about H3O plus, our hydronium ion. It's quite often used synonymously with H plus. They're really referring to the same thing. Just that when we have H plus in solution, it does react with water to form H3O plus. And so the reality is that H3O plus is what exists, but we quite often will just you'll see it quite often shortened to just H plus. And so sometimes you might see the net ionic equation for a strong acid, strong base reaction to be simply written as H plus OH minus yields H2O. So just be aware of that if you see that somewhere. We also talked about several gas-forming reactions. So for instance, a metal carbonate plus an acid yields the metal salt and carbon dioxide and water. And so for example, here's sodium carbonate, there's our metal carbonate reacting with hydrochloric acid, forming our metal salt, our sodium chloride, and then our carbon dioxide gas and liquid water. And another example was sodium bicarbonate. Metal sulfide plus an acid, so sodium sulfide plus hydrochloric acid, also is a gas-forming reaction. We form our metal salt, and in these cases with our sulfides, we form hydrogen sulfide gas. And some other typical gas-forming reactions. Gas-forming reactions are another one of our drivers of chemical reactions, something that will cause a reaction to occur. And we also talked about redox reactions, in which electrons are transferred between reactants. We talked about the oxidation is the loss of electrons. Reduction is the gain of electrons. Talked about a couple ways to remember which is which. Remember, Leo the lion goes grr. Lose electrons oxidize. Gain electrons reduce. Also, oil rig, oxidation is loss. Reduction is gain. And like I said, and this was a factor that we didn't really talk about in lecture. It goes beyond the scope of our class. But redox reactions happen because the resulting change is favorable for various reasons. And that's what drives these reactions to occur. We went through several different, all of our oxidation number rules. And so these are rules that you will want to be familiar with and will want to be able to use, because these rules are how we determine that an oxidation reduction reaction even took place. We have to assign oxidation numbers to every element within a reaction and see if they changed. And so we have to know how to assign those various oxidation numbers so that we can see if some redox actually took place. Did we have some oxidation reduction going on? And so we looked at four different basic types of reactions. We looked at precipitation reactions, where we're going to use our solubility chart and look to see if a solid was produced. We looked at acid-base reactions to see if an acid-base reaction occurred. You want to look and see if you can identify an acid or a base actually existing as our products, as our reactants. And in any acid-base reaction, we're going to end up with a salt, some sort of ionic salt, and water for any sort of strong acid, strong base reaction. We looked at gas-forming reactions, where we're looking for some gaseous products, and especially in the cases of carbonates and sulfides. So a metal carbonate or a metal sulfide plus an acid. And then finally, we looked at oxidation reduction reactions to identify if an oxidation reduction reaction took place. We need to identify if there have been changes in our oxidation numbers. Next, we moved our discussion into stoichiometry. Remember that stoichiometry is the study of amounts involved in a chemical reaction, and the heart and soul of stoichiometry, the center of it all, revolves around our conversion to moles. Because using moles is how we're going to compare one thing in our chemical reaction to another thing in our chemical reaction. We might be comparing a reactant to a product. We might be comparing a product to a reactant. We might compare two reactants. We might compare two products. Doesn't matter what two things we compare. But we're going to use our stoichiometric ratio from our balanced chemical equation to convert between moles of two different things in the reaction. The difference with any sort of stoichiometric problem is how we're going to get to moles, or where we're going to go from there. If we're given, for instance, the volume of some sort of pure substance, then we would have to use the density to convert to mass, and then use our molar mass to convert to moles. If we're given our number of particles, then we'll use Avogadro's number to convert to moles, and so on. And so really your overall pathway might be different, but it's always going to go through this central motif here of using our stoichiometric ratio to convert between moles of the two things that we're looking at. We looked at limiting reactants, and we in fact looked at several different ways of working with limiting reactant problems. Remember that in any reaction, one of the reactants will be the thing that limits how much product that we can make. And so we looked at different ways of going about that analysis. One way is our mole comparisons, where we compare the molar ratios of how much of each reactant we have versus the molar ratios that we actually need from our balanced chemical equation. We looked at one method of just carrying out the entire problem, just run through the calculation once based on one of your reactants, run through the whole calculation again based on the other reactant, and whichever one of those produces the least amount of product, that one is your limiting reactant, and that's how much will actually form. We also looked at the use of RICA tables. The nice thing about RICA tables is that if you have a problem that also asks you to identify how much of your excess reactant is left, the RICA table sets you up perfectly for that, to be able to have that information right there and find that out. We looked at reaction yields. And so when we do a stoichiometry problem, when we perform a stoichiometry calculation, what we're calculating is the theoretical yield. We're calculating if everything goes perfectly and I recover every bit of the product that I'm looking for, this is theoretically how much I would make. The reality is that you're never going to make that much. There are going to be some side reactions, maybe some impurities. Maybe you're just not able to recover all of it because of whatever your recovery techniques are. And so the actual yield will always be less than the actual theoretical yield. And so it's useful for us to think in terms of percent yield, to think in terms of, okay, how much did I actually get compared to how much I could have got? And so that's a simple enough calculation. Just take the actual amount that you measured, divided by your theoretical, and multiply that by 100. And then with stoichiometry, we looked at several different types of chemical analysis. We looked at a gravimetric analysis in which we form a precipitate, take the mass of that precipitate, see how much of it formed, and then use that information to possibly compare that back to how much of a particular reactant or a particular part of a reactant had to have been present. We looked at combustion analyses in which we can combust a hydrocarbon, collect the amount of carbon dioxide and water that we get, and using that information, we can backtrack that to find the empirical formula of the hydrocarbon that we started with. If we also have the molecular mass, maybe through mass spectrometry, then we can use the empirical formula that we get and scale that up to the entire molecular formula for the compound. And then finally, we also looked at titration, in which we have aqueous amounts of our product and reactant, and we're typically acid-base quite often with titrations. And we're looking to see, for instance, how much of a particular base do I need to neutralize an amount of acid that I start out with. And so all just various chemical analyses that we can do, which take advantage of stoichiometric principles. Lastly, we turned our conversation to thermochemistry and began to explore the energy involved in chemical processes. One thing that we looked at was looking at the surroundings versus the system, and remembering that we're always looking at energy from the perspective of the system. What is happening to the energy of our reaction? Is it gaining energy or is it losing energy? And that energy is going to flow either into or out of the surroundings. If our system absorbs energy, then heat is flowing from the surroundings into our system, into our reaction, and that is an endothermic reaction. If our system is giving off energy, then energy is flowing from the system to the surroundings, and that's an exothermic reaction. And so again, remembering that we're thinking of these energy changes from the perspective of the system, in an endothermic reaction, the system is gaining energy. Therefore, we consider the heat, we consider our Q to be positive. If the system is losing energy to our surroundings, then the overall energy of the system is decreasing. Therefore, we would say that is a negative energy change, a negative Q. We looked at using the classic energy equation, Q equals mc delta T, in which Q, our energy change, is equal to the mass of our given substance, times C, which is the specific heat capacity of that substance, times delta T, which is our change in temperature. And so this is an equation that we use quite a bit to calculate various energy changes. One of the something that we looked at using Q equals mc delta T is looking at the transfer of energy as heat. For instance, if we drop a piece of hot metal into water, then the metal is going to cool, the metal is going to lose its energy, the water is going to gain that energy. And we talked about how we can use that as these come to a thermal equilibrium, because eventually the temperature of the water will be exactly equal to the temperature of the metal. And what we can do is set up two equivalent Q equals mc delta T expressions, because the energy that the metal loses must be equal and opposite to the energy that the water gains. And so we could set mc delta T equations for each of those things equal to each other, again, recognizing that our final temperature in each case is going to be, in this case, to 23.1, because they will have reached a thermal equilibrium. So we can take advantage of that energy transfer and the law of conservation of energy to set up some equivalent energy exchange scenarios. We talked about the energy of phase changes and how, as we are moving, for instance, if we're starting with water at -50, we're starting with pure solid water. We start to warm it up until we get to 0 degrees. At this point, the temperature is not going to change. All of the energy goes into melting the substance. So all of our energy is going into melting our water here until finally we get to 100% water, 100% liquid. And then we're still giving this energy, and so we are now increasing in temperature until we reach the boiling point. Now we're going to stop with our temperature change again, and all of our energy goes into boiling the water, going from 100% liquid to 100% gas. And at this point, energy can again go into raising the temperature. And we talked about how we can calculate the energy change associated with this sort of phase change, how we would use the heat of fusion to calculate the energy involved with melting, the heat of vaporization to calculate the energy involved in boiling, but then our classic Q equals mc delta T for any of the heats where the temperature is changing. Making sure, of course, that we're using the correct C, the correct specific heat, for each different phase. But then when we do those calculations, so for our 5 different parts of our curve, we just add up those different Q's, and that would give us our total energy involved in this process. And then we started to look at thermochemical equations, where we can just simply write out the amount of energy involved in a chemical reaction. And so, for instance, carbon plus oxygen gives us CO2. That's an exothermic process where delta H equals negative 393.5. We also talked about a very important aspect of a thermochemical equation, that if we reverse the reaction, so instead of carbon dioxide as our product, if carbon dioxide is our reactant, so just simply the reverse of our first reaction, that's going to change the sign of our energy change. And that should just make intuitive sense. If going one way releases energy, going the opposite way is going to take energy. And so that's something that we have to take note of. We looked at using calorimetry to get thermochemical information if we need it, where we can measure we can run a reaction, for instance, in water, and we can measure the energy flow there. We can measure the amount of energy that the water either gains or loses through the course of the reaction. And that amount of energy change in the water is going to be equal and opposite to the energy change of the reaction. And so that's one way that we can get some thermochemical data of a chemical reaction. We talked about the use of Hess's law. For instance, if we want information about this particular reaction right here, but we don't have that, we're not able to get this through calorimetry, we can use two similar reactions. We talked about instead, if we know the energy information of this reaction here and this reaction, we can use that to get to the reaction of interest. And that's the very basics of Hess's law, that it doesn't matter which pathway we take to get there, the energy difference will be the same. The quantity of the heat is independent of the pathway that we take. And so this was a Hess's law example that we had. It looks kind of messy here, but that should look somewhat familiar to you, in which we were given two equations, one of them crossed out here, but we were given two equations and our target. And in Hess's law problems, we have to manipulate our equations however we need to, so that we end up with our target equation. And through the course of our manipulations, that might change our delta H values. But then at the end, we add them up to get our final delta H of our target equation. Lastly, we talked about using heats of formation in order to calculate an energy change of a reaction, in which if we are given delta HF values, if we're given heats of formation values of our products and our reactants, then we can sum up the entire sum of our enthalpies of formation, our delta HF of our products, minus the heats of formation of our reactants, and that will give us the heat of formation of our overall reaction. And that sums up everything that we talked about. And so hopefully this sort of brought things together for you a little bit and really sort of tied some things in a little bit and wrapped up what we've been looking at for the last few weeks. I would not use this slideshow as sort of the definitive slideshow of the whole unit. I might use this possibly to anything that was still fuzzy to you as you watch this. Shows you where you should go back and focus your efforts in as you study for the exam. I will talk a little bit more about the exam coming up. I just wanted to sort of like I said, to recap everything that we've talked about for the last few weeks, because we have talked about a lot. This definitely was a lot more information than we covered in Unit 1. This is a jam-packed unit, tons and tons and tons of information. And so hopefully this little recap and wrap-up has just highlighted for you some of the important aspects. So I hope this was helpful, and have a great day.